This is about graphing a transformed trig function. We're going to do the example of 2 sine 3 theta. And also describing, there's some key words that we need to describe the features of a modified sine or cosine graph. So what I've got here is just y equals sine theta. Remember, the key points to plot on that, when we're just sketching these guys, we don't have to worry about the points in here or the points in here. We just have to have the middle points, where it crosses the axis in this case, and the high and the low, the max and the min. And one crucial feature, of course, is that it repeats every 2 pi, and the terminology for that is it's periodic, and the period of the standard function without any modification is 2 pi. We're going to see that that changes when we modify it. And one thing I want to emphasize is that one way to think about these points that we plot, the 1, 2, 3, 4, 5 points that make up one cycle, they happen every quarter of a period. So like pi over 2 here is a quarter of a period. And we're going to see that that leads to a really nice method for graphing modified trig functions. So starting from this, let's say in another color, what should y equals 2 sine 3 theta do? Well, we figured out what individually those transformations did. The 2 on the outside, that's an output modification. What I like to say is we're about to give the answer with sine 3 theta. We've got a y value calculated. We've done all the interesting stuff, and particularly we've done this bizarre function sine, which we're still getting used to. And then we're about to plot a y value, and then at the last minute we just double the y value. That was the old y value. Here's the new y value. It's just double. And so if I take a point and I double the y value, it's going to stretch double in the y direction. Now a stretch means away from the axis. So positive numbers get bigger and negative numbers get more negative. So that's going to be a vertical stretch by 2, by a factor of 2. And then what about the 3? Now that's the one that's a little backwards from what people usually assume. The guess is often that that's going to be a stretch horizontally because it's attached to the input variable. That's correct, that it's input, but it's not a stretch. It turns out to be a squeeze. And we talked about in class how that's because you have to compensate for the 3. You have to divide theta values by 3 so that when you multiply them by 3, it's back to where you started. Okay? So it's a squeeze by 3. So it's going to get, like this point is going to get stretched upward but also squeezed inward. So we're going to get roughly something that's taller and something like this, taller and skinnier. Okay, I'm just doing it very, very roughly. Now, that's getting really, really busy, and so let's do it from scratch. The way to do these is not to start with a graph and then produce a lot of different slightly modified copies. That's often how you're taught to do this when you're learning transformations. It's not how to do it for real when you actually want to get the answer. So let's draw some axes. Okay, and let's think about those key. All we need to do is figure out where those key points went. Okay, so the key points. Let's put it over here with pretty writing over here. So, where do the key points go? If we can figure that out, we can just connect the dots in a nice sine curve shape. Okay, so what were the key points? They were 0, 0. And pi over 2, 1, and I shouldn't have erased the graph, I guess, and pi, 0, and 3 pi over 2 minus 1, and 2 pi, comma 0. These are the quarter period points. And of course the period of, I'm just going to reiterate it, y equals sine theta is 2 pi. We'll call it p for period, and we'll say that's 2 pi. Okay. And so a quarter of that is pi over 2 pi, all these, the 4 quarter points. Okay. So where are these guys going to go? They're going to get turned into, well, let's see. We know this is going to smush by 3 and stretch by 2. So if we smush by 3 and stretch by 2, well, the origin doesn't do anything. It's all smushing, stretching around the origin. So it's going to still go through 0, 0. And I have a name for this. I call this the anchor point, the start of the cycle. For a sine curve, it starts in the middle. Let me go ahead and resketch it. We're going to talk about this for a second here. Okay. So here's 2 pi, here's pi, here's pi over 2. The anchor point for a sine curve is in the middle going upward. And that hasn't changed. The other transformations that we'll do later will move the anchor point, and that's where it gets a little more complicated. Okay, pi over 2 comma 1. What do we figure out? You're going to squish it by a factor of 3, so that's going to move all the theta values smaller, but then the y values are going to get bigger. So that's going to go to pi over 6 comma 2, and this is going to go to pi over 3 comma 0. So I'm just taking 1/3 of the theta values, the input values, squishing them by 3 and multiplying the y values by 2. We're going to see an even slightly more efficient way to do this in a minute, but I want to motivate that by doing this first. And then I'm swishing this by 3, just dividing by 3 and multiplying. Well, multiplying by 2 doesn't do anything for that guy. Okay, so now I can re-erase my sine graph, because I really want to just have a cleaner picture where I just have the new graph. I guess the new graph was in red. Okay. And so let's see. Well, what values should I put on? Well, it's only going up to 2 pi over 3, which is even less than pi. So maybe I'd make pi like here. And we've got to have pi over 3 and 2 pi over 3. Whoops. This is going to be pi over 3, 2 pi over 3. And pi over 2 is in between. So you stick that in. And pi over 6. Okay. And then it's going to go from -2 to 2. I guess I'm using red. So I got it. Let's say that's 2. There's 1. There's -1. There's -2. And I'm just going to plot those points. So pi over 6 comma 2. Pretty steep. Then pi over 3 comma 0. Then pi over 2 comma -2 and 2 pi over 3. And now just connect them with something that's fairly nice shape. Don't make it too straight in the middle and too sharp at the corners. Otherwise, it's good. Okay, so that's one period. We usually ask to graph at least 2 periods just to get an idea of what's going on. We could go over here, or we could continue here. Let's continue here to see how that works. So let's look at what's been going on. Actually, let me give you a little bit of a different angle on here on this. Okay, so what's the period of y equals 2 sine 3 theta? What have we discovered here? How long does it take to get back to the start of the cycle? Well, the period was 2 pi, and that was sort of where this point was the end of a period. I've squished that in to be 2 pi over 3. And that's very general, is that we've squished all the theta values by 3, and so we're just going to get a new value for p, which is 2 pi over 3. So in general, the period of something that's of the form y equals a sine b theta is, we'll still call it p. What we do is we take 2 pi, which is the original one, and we divide it by b. This is a super, super crucial formula. You can always rederive it by thinking about these ideas, but it's really good to memorize because it's a great starting point. The reason it's a good starting point is that once you have the period, you can easily get the quarter periods. Just divide by 4 and use as a step, and just step by quarter periods. So in our case, we could have rederived this in a nice way by just say p is 2 pi over b, so 2 pi over 3, and a quarter period is then going to be that divided by 4, which is just pi over 6. Let me actually write that computation out. 1/4 times 2 pi over 3. and you just get a little cancellation. It's pi over 6. This is where I usually start out. I usually have people calculate the period and then look at the quarter period, and we're just going to step by quarter periods. Okay, so just step, an alternate way of getting these numbers is just step by quarter periods to get the middle, then high, then middle, then low point, and then middle again. And that ends out a period. So how would that look? We first calculate this magic number 2 pi over 3. Then we get pi over 6. And then we just know that if we just put tick marks every pi over 6, those are going to be the interesting points. And it's going to go middle, low, high. Now how high? Okay, well that 2, the way we figured it out before was it was as a stretch of the sine 3 theta function. Well, that's something we could turn into some official terminology as well. This distance, the fact that it goes from its midline up to 2, is an indication that it's twice as big as the usual sine function. So we could use 2 as a measure of the size, the bigness of that function. And that's exactly what we do. Okay? So how high or low above or below the midline do we go? That's called the amplitude. Okay, and in general, the amplitude of y equals a sine b theta is just, you just take this number a. It might be negative. We're going to see what happens when we have a negative in front here. But it turns out that we can just, for the size, is just the absolute value of a. We'll look at examples of that pretty soon. And so in here, in our example, oops, the amplitude is 2. Now it's important, the amplitude is not this minus this, not the top minus the bottom. It's the top minus the midline. Because we want the amplitude to be the simplest number possible, 1, for the standard case sine theta. So the amplitude is just how far it goes away from the midline. Okay, it's referring to the midline. Okay, and so that's the answer. That's another way to figure out what these numbers are going to be. Okay, so if we do this method of stepping through the quarter points, the quarter period points, we just have to know the amplitude, and that's how far we go away from the midline. Okay, so as we step through quarter period points, amplitude tells us how far away from the midline to go. Okay, so now I wanted to get back to the idea of continuing this one more period, and we're going to use this quarter period idea to finish this off. Okay. What if we're stepping by pi over 6s? That's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. They all can be reduced. And then 5 pi over 6 is this next one. And then we just continue the pattern. It was middle, high, middle, low, high, middle. Then it's going to go up to high again. We already know the amplitude is 2. Then 6 pi over 6 is pi. Next one. 7 pi over 6. And 8 pi over 6 happens to be 4 pi over 3. So 7 pi over 6 is time to go low. And then 4 pi over 3, we're back up. There's another period. So all we have to do is, these were gotten by stepping by pi over 6s, quarter periods. So that's a really essential way to think about this. Okay, so let me do another example. I know this is getting a little long, but it's not too bad. I'm on this limited version of screencast.com. Okay, well, I'll do it in another video. What I'll do in another video is I'll do another example from scratch using the quarter period idea instead of sort of deriving on the fly. But to summarize some of the important things, this idea is the period, which is how long one cycle is, and we've got a master formula for that. It's just 2 pi over whatever is in front of the input variable. Here I'm using theta. And the amplitude is just the absolute value of the number that it shows up here as a multiplier. What we still need to do is figure out shifts, like horizontal and vertical shifts. And that's going to be a little different. That's where the anchor point, which here didn't change, it was always the origin for a sine function. That's where that's going to change, but we can worry about that later.